Hey everyone. Yeah, basically the talk is about how we can leverage techniques that GPT uses underneath, like for our own domain, right? And basically we've seen the success and yeah, how this can be applied to something like malware detection. Yeah, a brief bio, why you should kind of, or at least like why be out there to talk about this. So right now I'm affiliated with Microsoft. This talk is not related to job I do there, but it's kind of a pet project we do with Luca. And so yeah, a bunch of like certifications, ICP, SANS, DEF CON talk on AI Village, Black Hat, and yeah, kind of PhD in University of Genova, where Luca is from for.
Hello, everybody. I'm Luca, assistant professor at the University of Genova, maintainer of like a library to create adversarial attacks against malware detectors. So yes, I'm the bad guy if you want to frame somebody. Well, it's me. And we have like some publication also like on quite number of conferences. One is like last year at NeRIPS, and then some European project on like testability of applications. But that's not the topic of today. Topic of today is going to be this one. So first, this is like a super short roadmap on what we're going to talk about. So I'm going to cover this, like how basically malware detection is done with machine learning right now. So without the things that basically Dmitrijs is going to cover later on. And then we're going to show you why this kind of things works in their domain, like natural language processing, and how it might be interesting for us as like cybersecurity people to, you know, somehow cover this domain, okay, the malware detection domain. And then that's going to be like, you know, the contribution of the talk, which is like how we do this in our domain, which is, I think, the thing for why everybody is here right now. Lastly, we're going to show some, you know, preliminary results, because this is still ongoing work, and some explainability, like why and what this thing is looking at right in the data, and what is something, might be something important for us. It can be used for other purposes. So this is the take home. So this basically is going to be the contribution. So this first giant blob is basically the network. Well, it's not HAL 9000, it's not like Skynet, it's just like a machine learning, like overly complicated machine learning model. But this is going to be what we're going to discuss today. And this is basically a nice plot that we're going to cover later that basically tells you what is important for the network. So in this case, you're going to see that there are some tokens or some words that are very, very important. Like you see, they are in red, because red, eye color means, whoa, this is very cool for me. Without further ado, okay. Let's start with, from the dinosaurs, okay? Like many, many years, from many, many years ago, what is machine learning for static malware detection, okay? So you have a PE file, which is, I don't know, it has a name, and it has something, it has structures, and from it, you extract from information, like, I don't know, which API is it called? It imports because it's static. You don't know if they're going to be called. Or which function will be export to the other programs. Or the contents of the section, like, hey, there is a string there called hello world and stuff, okay? And then you have like 1 million PE files, and you process them in feature vectors, which is just like a mathematical representation of them. And then you push them in a supervised machine learning model. What is supervised? It means, okay, this is malware, so 1. This is goodware, 0. Figure it out. Okay? So you give a bunch of like bad things, a bunch of good things, and then the machine learning model will try to put like a line between these two words. And that's what a supervised machine learning model is. And ta-da, then you have a probability. So these PE files now is like, wait, it's 95% probability of being malicious. Maybe it's really malicious, right? That might be like a ransomware. So this is nice, good. We are very happy about static analysis. It's fast, you can train it, but it has basically a lot of nice things that you can, think about. These are kind of features. I don't know, histograms, like you count how many bytes. Oh, the bytes number 0 is like 1 million times. And that's like a feature. Or again, sections. Hey, how many times the hello world string is contained in a section? You can think about it. And we keep going, okay? So this is just a recap slide on, you can be wild. There are a lot of papers that tells you how you should extract feature from PE files. So just don't cover them, all of them. So take it for granted right now, if you're interested in the slides. But, of course, this is like first part of the story. I'm just showing you these things just to let you know that these things are good, but not the best. First is, these are meaningful, but not complete. If you have like a bunch of bytes, and it's just bytes. They don't really say something about the execution. It's just a structure. Then, I mean, all of the people here are already thinking about like obfuscation, packing, and all other things. That at this level, well, it's messy, because if a machine learning model basically is trying to determine if something is good or bad based on random bytes. So not really good, right? Then you extract the features. You're like, oh, I have a nice histogram of bytes. But if I take the sample and go to Dmitrijs and say, hey, Dmitrijs, why this is malicious? He said, I don't know. This is just an histogram. So features are really not informative of the behavior. And lastly, as I said, this. So obfuscation, packing, whatsoever. I mean, you can basically restructure this thing at your will. And here I just point the fact that you can also do like nasty thing around the target machine learning algorithms, but this is like not the topic of the talk. Just saying that this is good, it's fast, you can train it like super easily, but it has a lot of limitations. So okay, another reason why this is like not really the best thing you would do is, well, this is the world right now. So you have PE files that runs on Windows, but you have also many other things that run on Windows. Like if you're just analyzing that PE, you basically cut everything from PowerShell script or VBA macros and stuff. And then if you're like in the PE, but then you have a server, a server on Linux, well, that model is useless because then you have Linux. And that model is completely useless because it's written to work with PE files. And then boom, what about those? I mean, how can you figure out if a living off the land thing on your machine is malicious or not? Like this thing, okay? So you have certitude that basically can download something and execute something. And the only way the only way you can spot this kind of thing is looking at the system logs. Like looking at these kind of things, right? And last limitation is you maybe won't have these files. Imagine that there is a compromised machine, okay? The only things you can really link into are the logs. And then maybe at some point you're gonna be able to extract from the, from the devastation that your malware caused inside the machine, exactly the culprit to extract the feature and put into the machine learning model. So these are the things that we would like to look into. And just to give you like another reason why static analysis is not maybe the best, is this is like the Dmitrijs attack matrix. There's basically all of the bad things that people around there can do. And just to mention, these are basically the most frequent one. And again, how can you say that your PE file, without being executed, does a process creation or a file creation or something? Maybe you can think about it from the API point of view, but that's not easy. So, you know what? Thank you, static analysis. You can, take your way out and just focus on dynamic analysis, okay? What is dynamic analysis? Well, you have basically a malware here, which is this amazing trustme.exe put inside a virtual machine, a sandbox, or an emulator, and then you wait, 5 minutes, and it's, whoa, I have this chain of events, like calling API 1, 2, 3, read, write. Well, you can think about anything. And then you have a report that tells you, hey, this malware, connected to x.y, or requested this from that server, or, wrote like a registry key. And lastly, even if these very, very, very trustable trustme.exe tried to is obfuscated, at runtime, at some point, it has to execute, the evil part. So from the static point of view, you would have missed that, but on the dynamic part, at some point, that API call would be called to some extent. So what is this pipeline up to? So you have your malware, then you put it inside a sandbox, so you basically you just load it, you don't care about how many sections it has. And then you see these kind of things, right? So you have multiple processes, or you have the DLLs that it loads and the APIs that it calls, and then you can see, oh, these are registry operation, and you keep going. These are not seen as static. Well, since sandboxes are kind of, wasteful in resources, what you can do is emulate them. We know that emulation is not the best thing in the world, but it's getting very, very good, okay? And relying on this, we're going to have basically this, but in a faster way. Because again, virtual machine, you have to basically reset the environment every 1 minute, every 5 minutes. It takes time. So we leverage this speakeasy tool. Maybe some of you already knows this tool. It's from Mandiant. Now Mandiant is Google Cloud, so it's Google Cloud. It's basically an emulator. So you give it a PE file, and basically there is like some Python code that run and that emulates it, okay? And the emulation is very good in the sense that, okay, maybe there are some some APIs which are not really mapped yet, but I mean, the number of the mapped API is very, very big. So we basically can use this speakeasy, and we take like, I don't know, 25K malware, and I don't know, 7K goodware, and we detonate it in a Python script. So you don't even need like a virtual machine, right? This is just to collect quality data and don't wait, I don't know, for like 10 years for somebody to release a new data set. Just to mention, that's like cool job by Dmitrijs, by the way. Basically, since there are some errors in the emulation, he basically patched a few of the API calls there just to improve the quantity of events and the quality of the events that you can trace. And this is the data set. So we have 70K malware sample from 7 different malware types. I don't know, Trojan, Dropper, some ransomware, and you can keep going. And on the blue axis is basically the number of files that were not corrupted by emulation. You can see these like a lot. So the number of errors given by emulation is very, very small. And I think that maybe, I don't know, some years in the future, this gap will, be closed. Because again, this is not like a tool like some students did. This is like a tool from Mandiant. So they're really putting, I think, a lot of effort in this research tool. So this is the data we're gonna use to train our, our very, very nice GPT model to, do malware detection. But how does data look like? So remember from the talks, these GPT models model language, okay? What is our language in this case? Well, this is our language. So let's say that there is a malware that, do something about network activity. So I would like a machine learning model to understand the language of reports. So there is like, like an API call that does server communication, and then there should be like an URL, which is the one that is contacted, and you keep going. Then you might have something, access to the registry, file access, writing. So this is the language we want to model, okay? Which is not the natural language. I mean, I think that nobody in this, around here speaks like to their partner, like APC0441E, like just to say hello. So this is not like the language that we speak, it's its language. We want to learn this. Wow, cool. Like, of course, there is a limitation. So the problem of doing this is that this language is a mess. Like, look at here. Basically, again, you have a lot of addresses and names and arguments and return values from the emulation, which are not really easy to cover, right? So how can a machine learning model make sense out of this, first? Second, these events are a lot. Like, you take 1 second of activity, and in human time, the only thing I can do is like putting this here, while in 1 second, a machine can cause 100 events, 1,000 events. And I just, I'm inventing the numbers, but I think they're realistic. And lastly, maybe not all of this is necessary. Because again, also like in our language, there are a lot of things that we can strip off, like, some articles or some adverbs that do really care when you're talking about. Having said that, I leave the stage to Dmitrijs, who is going to say how to solve these problems and show you more technical details.
Yeah. So basically, the question is, we've seen success, right, of ChatGPT solutions, and basically many of models are changing our lives right now. So yeah. Does this kind of apply somehow to us? And to talk about this, we really need to go into some basics. We not basics, but let's say fundamentals. We cannot jump over and talk about the details. So let's speak about how this stuff works. And of course, we are oversimplifying these complex concepts in 20, 30 minutes. But I think you will get the intuition behind it. So basically, first advancement to lead to success of this stuff, let's call it that way, is the architectures. And back in the day, in second decade of 20th century, we had convolutional networks and recurrent neural networks. Those date back to pretty long ago, actually. Luca published convolutions operations in 1999 on images, and it's basically computer vision stuff, where like specific parameter sharing goes over the 2 dimensions and extracts some features, for example, vertical lines. But we can apply this to like sequence of events as well, like textual data, and extract some patterns from text as well in 1 dimension. So I don't know, 3 kind of kernel with the size of 3 can extract something like exe, DLL, I don't know, ker, part of kernel 32, and similar patterns. And those actually work well right now, we know it. And they worked well in computer vision. Another stuff that really kind of was influential in AI field was recurrent neural networks. The most prominent kind of model of them was published in 1997 by 2, I believe, German gentlemen. I will not try to pronounce their surnames right. Yeah, it's basically a way to parse model like input sequentially, one after another. They have some problems by its own because you cannot parallelize the processing. But yeah, these methods dominated the field in like second decade of 20th century. Before that, we really were in the domain of classical algorithms. Now the deep learning came in with the neural networks. But everything really changed in 2017 when Google published a prominent paper called "Attention is All You Need." And that's it. They released the transformer model that actually strips away the convolution, strips away the recurrent, and they basically say attention is only what you need for modeling. And yeah, this is the image of a transformer model that everyone now uses to represent from the original paper. Yeah, so if you didn't heard this term, you are now, and yeah, this is the kind of big deal in AI nowadays. Yeah, and what is attention? It's basically an ability to do a weighted sum between 2 sequences, and it's of course a bit kind of complicated. It was queries, keys, values, but like on a high level of intuition, it kind of looks what is important for me from that other stuff that you are giving me, and this actually works super well, as we can see in many applications. And yeah, if we think about the world of AI in 2016. Every domain had its own state-of-the-art model. Let's say the techniques they used in every domain was different. Today it's like this, and so yeah, of course we have some tweaks and tunings, but the kind of transformer in the root of every state-of-the-art solution. Another stuff that helped those things to grow to those quantities we see now is the self-supervised language modeling. And that's how actually GPT is trained on whole internet. Yeah, like you cannot provide labels for everything, right? We have to task it to learn from data just as this. And how it basically happens. Again, 2 interesting works, not the first ones, but that kind of shaped our view on this is obviously GPT, original publication in 2018, which is basically a generative pre-trained transformer. And the BERT, which is like bidirectional transformer. And how GPT does. In scientific language or like official language, it's called autoregressive. It just goes and looks on the input in some context and just tries to predict what is next. In the simplest way, it's just predict me next word, like nothing, what's the next is. Nothing is nothing is impossible. And yeah, of course they extend it to predict passages or sentences, but the idea in the core is just this. That's how they learn whole internet, like as simple. Of course they do some additional stuff. Engineering, we will talk briefly, but not about everything. But in its core, it is this, it's 90-something% of computational power that goes into GPT models. BERT does it a bit differently. It's called masked language modeling, and so basically they take a sequence of events and mask some of them. And for example, in well-known sentence, if you mask it, like every one of us would guess, model is tasked to guess it as well. We kind of say it, what is in that place, and model should guess it. If not, we penalize it, and it slowly learns to understand what it should be. Those are 2 methods not only used for self-supervised learning. Actually, field is quite wider, but those are kind of the most influential and ones that used in most of the models in at least NLP, in natural language processing. Yeah, like let's go step by step how it happens. You have this corpus, right, of like internet. Everyone uses word GPT strength on the internet, but basically it's books, wiki, Reddit, and everything you can scratch like in accordance to copyrights and many other limitations. You do so-called pre-training stage. Yeah, that's why GPT has P in its name. And yeah, again, that's the 90-something% of computational power goes there. Then we have fine-tuning stage, where we actually still use supervised learning. Here we still need to have a like smaller but still labeled data set. It can be really anything, and it's tailored to actual application, like question answering. You have a question, and what should be answered? You get a chatbot. Like user recommendations. This user watched this stuff. What should we predict him next? And of course, malware and benign-ware. And yeah, then you actually operationalize the model. You deploy it to one of the applications. And you can have multiple fine-tunings of the same pre-trained model. So yeah, that's in general is how they do like all AI deployments today. Of course, there are multiple extra steps which we won't go into details. For example, GPT uses reinforcement learning on top of this. And yeah, we don't know what GPT-4 really does under the hood because it's concealed. But yeah, so kind of a lot of engineering around, but the core, it's essential to transformers and self-supervised pre-training. And since then, really just scaling up. And yeah, like models popped up like mushrooms after the rain, right? And what is the main achievement of, for example, of OpenAI in this direction is that they were not afraid to pour millions and to see how it works. Because before them, we really didn't understood that if you like train the model for $100 million, it will do better. So like no one done this investment. After them, like industry understood, aha, this thing scales up, and some properties emerge, and that's why everyone started to do this. And that's the field of computer vision. We have those perfect image generation stuff and the natural language processing. How this applies to security, right? Now we are ready maybe to jump back to our domain. And the thing, of course, we don't have capacity of like to replicate this scale experiments, but we still have, under some computational constraints, we can evaluate how those techniques work if compared to maybe techniques that we use today, or yeah, techniques that we know are the best now. And that's where this model comes in. This part is actually what Luca described already. We have a dynamic analysis, and we extract the behavior. But we argue that it's not limited only to malware detection. Basically, any log that you have in your SIEMs, in, I don't know, CloudTrail, basically any this type of data can be adjusted in a similar way. It's a speculation, but we believe it, and we work to prove it as well. We collect alternative data sets right now. But you get the behavior, right, in some way. Then what we argue is important, it's data cleaning. That's the actual stage where you guys come in, where the security domain knowledge or the domain knowledge of actual behavior is needed. Because AI folks don't know this. They kind of will take as is, and they trained on whole internet. And we argue that we need to clean data, and based on our observations. So this is Speakeasy report that, as Luca discussed it. Problem first, you have too lengthy sequences. You cannot just go and work with them as is. Transformer is really sensitive on the sequence length, so you have to deal something like somehow with that. So yeah, for example, we still didn't discuss what are tokens. We will be in a moment, but if you look on a number of unique elements, you can consider as unique parts of the JSON. If you don't do any filters, you'll get around like, in just our data set, we get close to 1 million of unique elements. And if you apply like simple filter, like let's parse only API calls, you get about 20,000. So it's like the plots scale is logarithmic. They are just not close like completely. So yeah, you need to apply filters, and that's what we see. Like right? For us, it's intuitive. We see the memory segments, and we understand that this doesn't generalize to whole malware behavior, for instance. It's just an arbitrary value that appears at the moment of execution. And it can be any other memory segment. Like, it's completely arbitrary. The same applies to hashes or like the similar patterns. So, and that's what we see. If we strip away this data, if we leave it, the performance drops. This is a rock curve, and like we can assume for now, the higher the better. And we see if we don't do any filters, like performance drops drastically. You will not get anything. So you need to apply domain knowledge, at least at the current state of things. Another, what we preserved, basically it's obvious to us. It's like the API calls, file access, registry, and network. That's essential core that we need to analyze malware. Everything else like goes away. Another thing that we do during this step is normalization. And for instance, if you look at this file path, I don't know if you see the laser. So like in your head, it pops up. Like you have system32, hash, and that, right? The model don't know that. It will go char by char, or will try to interpret this token independently. So we do this for model. Like right now, it's not yet ready to understand it on that level of kind of, association with that this is a hash, and any other value that will be the same length and having the same characters is hash. So you have to say it. That's why we introduce some placeholders like IP addresses as well are not valuable per se. Those are just keys to something else, right? And we normalize to, in a broad terms, like it's public, it's private, it's loopback, and some other stuff comes in. Now, we go next stage, feature extraction. And that's actually where we are roaming into the domain of how GPT does the things. It consists of tokenization and encoding, and it is ubiquitous to any NLP application. What is tokenization? You have a sequence of something, right? Sentence. And you need to divide it to unique elements, tokens, which are sort of atomic units that are not splittable further. In case of sentence, we can think those as words, but not always. And actually, like systems like GPT does it a bit differently. I will show in a moment on more a statistical manner. But further, you split it to tokens. You need to encode it against a specific vocabulary. So what it means, you just take a token and do it like in an integer manner, like you assign it a label. And then label is not useful for model. And industry came up with the concept of embedding, which is basically one label, but extracted to a higher dimension. You can assume it's not one number, it's like 98 numbers, which are dynamically updated during the training. And this yields interesting properties. So similar tokens in that high dimensional space appear in a similar locations. For instance, two API calls that does the similar stuff, for example, read a file, will be located in a kind of similar direction in that high dimensional space. How we do it with the Speakeasy, we take a JSON file and like in a flat manner, just go token by token. We strip away some of them, like keys, for example, in JSON. We don't need them to provide every time for a model. Model will learn based on the sequence behavior, not by the specific patterns. And we actually don't use those white space tokens when you split by spaces. We use so-called BPE tokens, which actually how GPT works as well. They use byte pair encoding. It's like they see whole blob of data and try to find which characters occur more often together, and they group them based on this co-occurrence. So it's kind of the stuff that it learns automatically what tokens are valuable, which is super useful for our data, actually. And now we are ready to model, right? That's actually where transformer comes in, and at this stage we pour this embedded behavior into the transformer. And how we evaluate, like, how well those techniques behave on our data. So you have to work with some subset of data. You cannot just take anything. In data science, it's denoted as training data and test data. What we have in January, we collected last year about 70,000 samples of training data, and test data comes from April. So like to represent the content shift in malware behavior, at least partially. And yeah, we chose a large part of the training data to be this unsupervised. Like we strip away all the labels. We don't know, is it malware, is it goodware, and try to use this large chunk of training data just for like not using any labels at all, and pre-train it using MLM. Actually, not like GPT does it, but like the bird does it. Because GPT pre-training is more suitable for generative tasks. You give it a context, and it generates something further, like ChatGPT, right? Chatbot. In our case, we just need an inference. It's like when you generate a representation and get a label. Like, is it bad or is it good? In that case, MLM works, at least it's more tuned to this type of logic. You still can apply autoregressive stuff for inference, but yeah. And yeah, we do actual like masking of tokens. You hide some of the behavior of malware or goodware, and you just ask the model what's hidden. It's just to reinforce what we actually do. And after that, we fine-tune the model on smaller part of data. Yeah, it's chosen based, we will see in a moment. And yeah, evaluate on the test set how this model that is using, for example, that pre-trained the unsupervised blob, how it behaves if compared to that one pre-trained, for example, without the pre-training, just using the orange part of data. And that's what this graph represents. Here, the orange line is the performance of model that used only this small blob, no pre-training. The green part we still added. It's a baseline, sort of perfect behavior that we can get out of the data set if we knew labels for all data. And we know them during the experiments, but we strip them away. And this blue one is actually one that uses the variable part of the unsupervised. And that's what we vary. On the left side, we have this unsupervised data as big as the supervised, just to check how it behaves. And on the right part, we're going to make it the most possible out of our data. It's 5 times bigger than the supervised part. And actually, what we see is that, jump too fast, sorry, that when you use actual, like all data, that without labels, it matches almost the performance as if we would use labels. Like, the idea is that we actually don't need labels that much, and we can use the masked language model to just, in huge amounts, the data that we store in our seams, to kind of update the model before we actually go to the application itself. And yeah, we compare how it behaves to known alternative techniques. We really cannot compare to like commercial AVs or EDRs, because how like AV or EDR performs. It gets a sample, it does some Yara check rules, it does some static analysis, and then it ships it to cloud backend, does the dynamic analysis. So it's like a sequence of micro checks to do like inference based on whether the P is bad or not. In our case, we found some at least publicly known solutions that do specifically a dynamic analysis, which like 3 of those actually are based on the convolutions, and ours, we call it Nebula, is based on the transformer. And we see that it like outperforms with a gap those like classical methods. If you read those are the ROC curves, and you can like guess for example, specific fixed false positive rate, like 1 false positive in 100 checks, and you can get like how much of samples do I detect under that. And we, for example, detect close to 80%, like 75, and yeah, the closest competitor, only half of the samples are detected in our data set. In our test set, actually, which is like even farther in future. But again, it's just limited data, limited time constraints. You can scale it up and get better results. So another bonus part that we get from transformers is that we kind of can peek into the model and kind of get out what it does. And we just took a random sample, the backdoor, I believe it's urelless Trojan, and we took a look what actually activates in a model when it goes through. And we see, for instance, the strongest activation is between those two tokens. It's like exadose, which is fun, because exadose is not something seen in a default system, but it consists of those exa and dose, right? And might be an attempt to evade some detection, because like maybe tired security analyst will slip through it, or we don't know why the authors of this wonderful malware sample use it. Then there is the get tick count, which is an API call actually known to be used in anti-debugging based on timing, right? There are manual rules. For instance, this one is from, FireEye, again, Mandy and Guy, who wrote the Kappa rule for that. And the function looks like something like this, whether I am debugged or not, based on the get tick count. So like to check, maybe continue execution or not. And interesting thing, for example, the same sample but different segment, we compared what attention shows with the existing state-of-the-art technique from explainable AI domain. They have some mathy methods how to guess what is done under the hood, and they kind of align together. We see that in this segment, the ini file that is dropped to temp folder, then the malware access the file in a Windows folder with name as a hash. That's what I actually showed before. And both methods kind of associate this with the malicious behavior. So this indeed kind of can yield an interesting maybe insights to cluster the similar malware types and families. So yeah, looks like that we can use this information for further analysis. Maybe even we can get new indicators of compromise. For instance, the color is different, but it still indicates maliciousness. It's just from different attention head. But we see that return value from TLS get value API call, for some reason, has super strong activations within arguments passed to this white chart multi-byte API. And we couldn't, at least with our knowledge, identify why this might be bad, what this represents. But yeah, maybe for a good reverse engineer, this might be a good hint and lead to a good IOC they can deploy somewhere. So yeah, it's again speculative guess, but might be. So yeah, summary. Woohoo, you survived a lot of concepts thrown at you out of your information bubble. And but we hope we get the intuition how this stuff can work and can be applied to our direction. And what we argue, that you actually need logs to detect stuff, right? And logs are ubiquitous. Any system generates logs, any application generates logs. And they are sort of all similar. They are timestamped, system, machine language stuff that represents that something happened. And we can model it with a little bit of domain knowledge. We can model it with modern AI techniques. And that's what we say. Currently, solutions, this is not perfect, might be, and needs more work. And we don't yet have super efficient solution, but this is an insight what might work there. And we publish all this information, data set is public, the code is public, so you can grab it, and if you are interested in a topic or migrate it to another domain, to another data, feel free to look, everything is open. And what we see that Transformer indeed rivals, even in this domain, sort of how we do stuff, and might come in to our applications in the next few years. And the main thing that we think is super important is that we can use the self-supervised stuff. We finally can utilize terabytes of those logs that sit in our SIEMs and wait when actual detection engineer will type process parent title is this and process child title is this and this is bad. So we actually can start maybe pre-training models without person going there. Yeah, right now it's just supervised. So yeah, that's it. Any questions? Yeah.
All right, thank you very much. Any questions? I'm seeing a hand here.
Oh.
Which one do you want? This one or this one?
Hey.
Yeah. Thank you for the great talk. My question is, maybe I missed something. the data set you used for training, how did you arrange that it's like split up 50-50? So like for like true positives, false negatives, and so on?
Yeah, it actually wasn't split 50-50. We, let's go back to that error plot, right? I can show you how far it is.
No, I think it's
Already went over. But we collected more malware samples than cleanware, benignware, or how you name it.
Okay, but then the evaluation is 50-50, right?
It really, even evaluation is not 50-50. But it doesn't, it's important that it's not completely skewed. Like, we have 1,000 cleanware and like 90,000 malware. It still can be like, in our case, it's about 25 to, yeah, maybe 30% benignware, which is benign here. And the rest are the malware, which is still more than benignware, but it's it's maybe 40-60, maybe 30-70. So it's still a skewed data set, but it's not a problem for evaluation. You still get fair results if you want for false positives and similar stuff.
All right, thank you.
Yeah.
Any more questions? There in the back.
okay. So
Do you hear me? Okay. So about the part when you try to explain how the attention module works, can you please give me more details about which attention modules do you use? Because as I've seen, your transformer uses 24 layers, which is quite huge.
How many layers? Two layers, actually.
2 layers, okay,
Yeah.
sorry. Do you look at attentions in the first or in the second layers? Because that changing a lot of things. Oh, sorry. Do you understand what I mean?
You ask whether...
maybe it's too technical, sorry. You have a multi-attention layer. How many heads do you have?
heads, number of
Heads, I see. Yeah. There are two, like, encoders. So we've seen this stuff, right?
Yeah.
This image that appeared here. They are stacked, two of them, and this is actually a really small number. Usually you would stack them more. We stacked only two because we want to compare to all those other models, and we wanted to match their size. We didn't want to expand. Usually you stack 16 maybe encoder layers. And in each encoder there are 8 attention heads. We use 8. I believe you can, it's sort of close to standard. Usually you use about 8, maybe 16. And in one of those attention, they are processing independently input, and each of them learns one stuff that they think is important. For instance, what we showed is this, right? Activation from red was an activation from one head, and blue was activation from another head. Oh. Yeah, but you get what I mean. Yeah, this is from one head, and the blue is from another head.
Okay, another question. How many parameters your model has? Does your model have more parameters than the number of samples? Or
sorry.
Yeah, it's 5 and 6 million parameters, I believe, and samples are 70,000 or something. Yeah, or total. Yeah, and training's at 70,000. Yeah.
Thanks.
All right, there was a question.
Hi.
Hey.
As you on the last slide said that most of the industry is not applicable and does not apply your research here or this kind of stuff you showed us. Do you know if and to what extent some of the big players of endpoint protection and EDR, XDR solutions and so on and so forth, so for example Microsoft, who is very strong behind OpenAI and so on, does they use this kind of techniques already? Do you know?
Spoiler alert.
Let's say I have some internal info that Microsoft tries to build I don't know if it's for record.
No. You can talk freely.
Yeah. It's not NDA stuff.
It's off the record. No problem.
But let's say at least nothing is published publicly. Nothing. Like there's no work that could say, hey, we use this and this is how. I think under the hoods they do something on system logs, but mostly if you hear something like this, it is the like attempt to try to use existing LLMs that trained on natural language, not on this type of system log language. They use GPT. GPT is still good in technical language. You can pour it code and it pours it back. It still can kind of say you something about, I don't know, Sysmon or ODD. You throw it and say how this behaves. And mostly if you hear some applications, it's kind of usually is the using sort of GPT type, kind of only on API level. They don't work with models. They have an API call. They do it and they get some response, and that's how we apply AI in our like solution. But so that someone could use the system logs or this machine language to pre-train, we can at least not publicly, definitely not. At least to our knowledge, maybe.
If I can jump, can I just add?
Yeah, yes.
Another thing is like if you do some research, like among like the publicly available white papers of the companies, most of them say, yeah, we have machine learning, like give us $. Then you can, if you just start to scrape a bit on the iceberg, then there is nothing like this complicated. Maybe you have like some very easy static machine learning model. Maybe it's already inside your PE and you don't even know it. And then maybe you start digging more, and then it's basically, I don't know, linear model from the 80s, first thing. Second thing, the only like big advancement that we saw like in the last month is the model that is basically shipped by Aristotle to try to explain some malware, but it's only for PowerShell scripts. And it's not detection, it's just like, oh, this PowerShell is malicious. Oh, thank you, that's why I'm uploading that to you. So that's the thing, basically, which is important, but we are not here yet.
Okay, thank you, because the way I thought about it is that I would assume that Microsoft is a very prominent partner or a player in the field to just use this, because Microsoft has the power, has the samples at least, have the addict to the OpenAI or the machine learning stuff, and maybe they know a bit about what's written in the log files and so on. So they would be a very good candidate to just apply those techniques. Yeah. Okay, but thank you. Maybe later on the beer.
Yeah. Thanks.
All right. Any more questions? No? Then thank you again for the interesting presentation.
Cool.